Hi boys and girls, Vasha and Vidya. In the last video, I told you about the need for digital modulation, why the discrete signals cannot be transmitted over an antenna, and why digital modulation is important. And you learned the names of the digital modulation schemes like amplitude shift keying, frequency shift keying, and phase shift keying. And I told you the importance of phase shift keying. Now, in today's presentation, we will see the three types of shift keying schemes, the modulated signals and a comparison between them, and we will say about BPSK, which is very important in mobile communication. So with that introduction, let me invite you all to that today's presentation. Now let us understand this ASK, FSK and PSK signals. So what are the objectives of learning here? First thing, you will review the operation of a digital modulator. Then you will learn the ASK, FSK and PSK signals. Then you will learn the difficulties in ASK and FSK modulation and the significance of PSK, especially BPSK. So if we consider digital modulator as a block, as a black box, what is coming at the input are the bits, incoming bits are there, and outgoing, that is a modulated sinusoid. So for corresponding to each bit or bit pattern, we will have modulated sinusoids going out. So they can be easily transmitted over communication channels or through the antenna. The first thing, shift keying method is amplitude shift keying. As I told you previously, here the amplitude of the carrier is being varied according to the bit pattern coming. So suppose that the input bit pattern is an alternating zeros and ones, like 0, 1, 0, 1, 0, 1, etc. each with a duration say 100 nanosecond. So in this figure, if you see here, so say this is a low duration, that is first 0, from here 0 to say 100 nanosecond, okay. Then it goes high from here to here for another 100 nanosecond, then low for another 100 nanoseconds, etc. So this red curve shows the input bit pattern. And here this blue curve shows the ASK signal. So for this 0, corresponding to the 0, I have one amplitude, say 1 millivolt. For the 0, I have a 1 millivolt, and here the my bit becomes 1, so it goes to say 3 millivolt. Okay, and again here it's another 0, so that's a 1 millivolt, and so on. So ultimately what I do is my carrier has two amplitudes. One is corresponding to the logic 0, I have one, and corresponding to the logic 1, I have another amplitude. It doesn't matter which is which. It can be 3 millivolt for a 0 and 1 millivolt for a 1 as well. So this is how ASK signal looks like. Now, as you all know, the amplitude component is always very susceptible to noise. Probably if you remember the amplitude modulation, the analog modulation, it's highly susceptible to noise. So it is quite noise prone. So again, maintaining different power levels, different amplitude levels in transmission is a very cumbersome procedure. So ASK is rarely used, but a variant of that called quadrature amplitude modulation, that is very popular. Unfortunately, I think this is not included in your syllabus. Then comes the frequency shift keying system. That is, here instead of using two amplitudes, we use two frequencies. Say here, again I use the same bit pattern 0, 1, 0, 1, etc. Each lasts for 100 nanosecond. So this is the first low, that is from 0 to 100 nanoseconds. So that is represented by a low frequency sinusoid. So this from here to here, the duration is 100 nanoseconds. So this should be there are two cycles in this, so that should be 20 megahertz. Okay. So for the low the zeros, I'm transmitting a 20 megahertz, and for the high, you can see that there are four of them, four cycles in 100 nanosecond or zero point 0.1 microsecond, so that should be a 40 megahertz. Okay, so this is how an FSK signal looks like. So probably this reminds you of the FM signal also, although the analogy is not exact. Here the idea is just for one low I transmit one frequency, and for the high I transmit another frequency. It doesn't matter which is which. It can be a low frequency for a high and a high frequency for low. It does not matter. But what matters is another thing. So how this is generated? It is how do we generate frequencies? That is traditionally by oscillators, but nowadays people don't use oscillators. Instead, people use frequency synthesizers. So what we do is, depending on the bit pattern received, we generate one frequency or the other. So a frequency synthesizer is allowed to be switched between two frequencies, two preset frequencies. One problem there is it causes a phase mismatch during switching. So if you look back in this signal, you can see that this is a point where it switches from a low to a high, or this is from a high to a low. But here if you see, this is almost continuous, because here there is no phase discontinuity. This almost merges, this 20 megahertz signal almost merges into this 40 megahertz signal. But here they are harmonics. Even then I cannot say it is a perfect coupling is there, or perfect continuity is there, but here they are incidentally they are harmonics, and it looks like a continuous phase one. But in reality, in the actual practice, it's very difficult to obtain continuous phase modulation like this. Instead, you will observe discontinuities in phase. So getting continuous phase FSK is a very challenging task. So that makes FSK very unpopular. There are many other reasons also. But there are some variants like minimum shift keying. It is still in use in MSK modems and all that. Earlier, this was very popular. I remember one of my, when I was a UG student, one of my fellow team of two people, they were making a minimum MSK modem in using C programming. That was quite a hectic task at the time. But nowadays, it's a lot easier. But at the time it was very significant, but nowadays the significance is less, but it is still being used. Now comes to the third variant, that is a phase shift keying. Here, instead of using a frequency change, it uses a phase change. There is a PSK signal that contains that uses two phases for the carrier corresponding the zeros and ones. See, if I look at this diagram again, I use the same bit pattern: 0 for 100 nanosecond and 1 for another 100 nanoseconds. So you can see that from here to here, I see the carrier sinusoid coming here. Now it makes a transition from 0 to 1. Now the phase reverses by 180 degree. Okay. Again, the same frequency, but the phase is inverted by 180 degree at the transition at this point. So again it comes here, again it makes a transition from high to low. So there is a phase reversal by 180 degree. Okay. So whenever my receiver encounters a change in phase, it detects that there is a change in bit also. So this particular scheme is called binary phase shift keying scheme, or BPSK system. So PSK is generated by changing the phase of the carrier depending on the bit received. So if I'm using bit 0 and 1, then I can easily change between two phases, say 0 phase and pi phase, as we saw in this case here. This is a 0, and here I have a phase of 0. Now when it encounters a bit change, a bit transition, now it reverses a phase, and now there is an additional phase by 180 degrees, so pi phase. That system is called a BPSK, or binary phase shift keying system, or BPSK. Now suppose I can have four phase values also. Instead of using only two phase values, I can use four phase values. So one popular scheme is by using four phases, like phase of pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. They are used. That scheme is a modification of the binary phase shift keying scheme. That is called the quadrature phase shift keying system, or QPSK system. Now, to which are these four phases attributed to? Here, a 0 phase is attributed here to bit 0, and pi phase is attributed to the bit 1. Now, there are four phases here. Which are they attributed to? They are attributed to pairs, like suppose I take two bits at a time, and this may correspond to a 0 0. The transmitted bits are coming into my or the bits to be transmitted come to my digital modulator. So I take the first two, and if it is a 0 0, I assign a phase pi by 4. If it's a 0 1, I may assign a phase 3 pi by 4. If it's a 1 0, I assign a phase 5 pi by 4. If it's a 1 1, I assign a phase 7 pi by 4. It may not always be in that sequence, so that is one possibility. Even though QPSK is there, BPSK is default modulation in mobile communication. So you are all using mobile phones. So the carrier, that is the digital modulation that is being used is BPSK in all systems. Now coming to what you understood in this short video, first you reviewed the operation of a digital modulator. Probably you remember that block diagram. What it says is it converts a binary stream. So if I consider a digital modulator as a black box, what is coming in are the bit stream, and what goes out are the modulated sinusoids that are ready to be transmitted through a communication channel or an antenna. Now you understood the ASK, FSK and PSK signals, and made some rudimentary comparisons. And you understood the significance of BPSK in mobile communication. So that is the end of the presentation. Bye-bye.